So in this video, we'll be talking about resonance, and this might be partially review. I think it will be going into a bit more depth than you've had in your general chemistry class, but this is a pretty important topic and will be coming up a lot in your 2 semesters of organic chemistry. So what is resonance? When there are 2 or more valence bond structures possible, differing in only their placement of electrons, the molecule will show characteristics of all possible structures. The different structures are referred to as resonance forms, and the actual molecule is said to be a resonance hybrid of all its resonance forms. They do not exist on their own, hence why we put them in brackets, and I'll show that in a second. And when we're showing resonance structures, we'll show a movement of electrons, and we represent that by using a double-headed arrow to show where the electrons are moving to from their original location. So let's look at this charged organic molecule. And as I'm drawing this out, what's kind of important to note is this is sort of a condensed molecular formula representation, and just because the oxygens are shown right next to each other, that does not mean that is how they're bonded in the structure. I encourage you to try drawing this out on your own with the oxygens attached to each other and see if you can come up with any reasonable formulas, because I don't think you will, without breaking octet rules or having more charges on the molecule than before. In general, like I mentioned previously, the more charges on the molecule, the less stable it is. So if we're going to show the resonance form, just forgot the brackets, we use this sort of double-headed arrow here to show that these 2 structures are in resonance. So we have the charge on the oxygen here. And if we're going to show the movement of those electrons, we would show a double-headed arrow, right? So the electrons are moving from one of the lone pairs, doesn't matter which one, show an arrow moving from one of the lone pairs towards this bond between the carbon and the oxygen, right? And if we do that, right, you might say, oh, there's a bond here, another bond here, 2 bonds here, and a bond here. That carbon has 5 bonds, as breaking the octet rule, right, because it would have 10 electrons around it. So to make sure we're not violating anything, we have to show the breaking of another pair of electrons. And we don't typically break sigma bonds like this, right, because they're very strong, but pi bonds are higher in energy, and they are more they are going to be the thing that breaks when we're doing these resonance structures. So that's important to keep in mind. So we're going to show the movement of electrons from the pi bond toward the oxygen, right? We're not breaking the sigma bond, we're breaking the pi bond. And so we have to draw that structure again. And now the double bond is on this lower oxygen. And the oxygen up here now has 3 lone pairs. So what about the negative charge, right? We have to make sure that negative charge is retained in this resonance structure, right? So it has to go here, right? From our formal charge rules, oxygen is neutral with 6 electrons. There are quote-unquote 7 around it, right? Because it owns one of the electrons from this bond here. So 6 minus 7 is -1, so it has a formal charge of minus. Right, and so the charge isn't like bouncing, quote unquote, from this oxygen to this oxygen. It is because the electrons have moved, and there's more electrons on this oxygen. The negative charge ends up here. It didn't move. It is the oxygen now, because of its electrons that it has around it. It now has a negative charge. So, right, these are resonance forms. And there's no difference between these structures. We'll see in a little bit that sometimes when you move electrons around, it'll end up on a different atom than before, and there is one resonance structure that's preferred over the other. But in this case, these resonance structures are equivalent. So how do we represent that? We would draw something like, zoom in a little bit here, so it doesn't appear as crowded. We draw something like this, where instead of having straight double bonds, we would draw dashed bonds. Not quite the same as the 3D structural space, but does this mean that there is partial double bond character between these oxygens. So what about the negative charge, right? So we would draw partial negative charges, just like with the dipole moment example in the earlier video. So this shows that the negative charge is equally spaced between the oxygens, right? It's being equally carried by both oxygens to indicate the delocalization of charge, right? So spreading this negative charge delocalizes it, right? So this structure here is more stable than it would be if the entire charge was located on a single atom. So we call this the resonance hybrid, right? So let's look at another example of this. So when we look at resonance, we can also talk about MO theory a little bit, right? And what I mean by this is we can look at the delocalized molecular orbitals over several atoms. And this can be done for charged molecules or neutral molecules with atoms with a lone pair or available pi bond next to sp2 hybridized atoms. So we're going to look back to this acetamide example that we gave earlier when we talked about that exception to the hybridization rule, right? So let's go ahead and draw out acetamide again. You notice, even though we talked about line angle formulas earlier, I am drawing in the carbons. That is kind of just for clarity in these situations. So, drawing it spatially correctly, we have this, right? And so the way I have it drawn here, right, kind of like we previously discussed, we're suggesting this nitrogen is sp3 hybridized, right? But if we remember, it should be actually sp2 hybridized, right? So, I'm actually going to erase what I've drawn. So if we're going to draw the resonance structure for this, right, we're going to show the lone pair on the nitrogen moving to the bond between carbon and nitrogen, and the bond on the oxygen, the pi bond on the oxygen breaking onto the oxygen. So what do we have here? Right? So you have to make sure, because this double bond was broken onto the oxygen, it now has a formal charge of plus or of -1. And now there's a double bond between the nitrogen and the carbon, right? So now what does this nitrogen have? Is it neutral? It shouldn't be, right? Because we have a negative charge here, so it has to be balanced out. So even without thinking about formal charges, we know this has to be +1, right? Because the bond connectivity of the carbon didn't change, it still has 3 sigma bonds and 1 pi bond, so the only thing that changes is the nitrogen. So again, thinking about formal charge, we know the nitrogen has to have that +1. And so the resonance hybrid for this would be as follows. Right. And again, showing the partial double bond character, we do this. And we can say that the oxygen has partial negative and the nitrogen has partial positive, right? So when we look at this, is one of these structures more correct than the other? And the answer here is yes, right? Even though in both cases, the oxygen has its octet rule satisfied, the nitrogen has its octet rule satisfied. So there's nothing really wrong with this structurally, but there is charges here. And with less negative charge, or with less charges overall, we have a more stable molecule. So we know that this is the major resonance structure. And this is the minor resonance form. Right? And the important thing to know here is if the nitrogen was sp3 hybridized, it wouldn't be able to transfer its electrons into this bond here. And it kind of ran out of room for this page to show you that, so I am going to erase what I've drawn. So I'd recommend either getting a second piece of paper or on the Word document, just spacing things out a little bit so you have more room when you print things out. But I will erase things now. I apologize, that is my own fault. So let's take a look at the molecular orbitals for these, right? So we have some more in-depth explanation as to why that nitrogen cannot be sp3 hybridized. So I'm going to draw things a little bit funky to sort of show some planarity here. So if the nitrogen here was to be sp3 hybridized, now let's draw it like this, right? And we'll have a lobed lone pair. And I've just drawn the sigma bond between the oxygen and the carbon. So its pi bond is above and below those two. Now we have this. So that is that pi bond between those two molecules, or those two atoms. So the nitrogen has that lone pair. It's pointed away from the rest of the molecule. It's pointed away from the rest of the molecule. So it cannot donate its lone pair into the system, right? It cannot help to delocalize that charge, right? As an sp3 hybridized, there would be no overlap, right? So the way we would draw it instead would be as follows. Like this, boom, boom. And now the nitrogen has, because we've drawn it sp2, like, it has an unhybridized p orbital that is now containing the lone pair. So let's go ahead and fill in those lobes. Actually, what I'll do, just to sort of, for clarity's sake, go ahead and draw the electrons like this. And instead of having the two dots for electrons, I'll show the actual lone pair here. So the lone pair is now occupying an unhybridized p orbital, right? And now you can see that there's overlap, right? That can happen between these three unhybridized p orbitals on each of the atoms. So we can show the connection like this. And so what I'm kind of showing here is not the individual resonance form, but this is sort of showing the resonance hybrid, right, that's taking place across these three atoms, right? And so this is why the nitrogen has to be sp2 hybridized, because it wouldn't have this overlap otherwise. So it has to be in the sp2 state. So even though the most stable resonance form was when it was neutral, right, there is still that minor resonance contribution from the resonance form with the double bond on the nitrogen. So if there's minor contribution, that means the nitrogen has to be in that sp2 state to even achieve that. So that's why nitrogen, shown here, has to be sp2 hybridized, right? So this requires the orbital containing the nitrogen lone pair to be aligned with the carbon-oxygen pi bond. All orbitals overlapping is the most stable form. So that's why the nitrogen adjacent to the sp2 carbon is considered itself to be sp2 hybridized and with trigonal planar geometry, due to the resonance contribution that it gives. So it's kind of like a really in-depth example as to why the nitrogen is doing what it is, and why atoms with lone pairs next to sp2 atoms are themselves sp2 hybridized because of the resonance contribution that they can give. So I hope that makes sense. I know it was kind of a little in-depth, but I think it's good to kind of recognize that and kind of see why it is doing what it is. So back to general rules for resonance. So, it's kind of a big list here, and I won't go into incredible detail with everything, but these are just kind of the general rules, right? And we'll be going through a lot of examples of resonance structures in order to get the best experience we can with drawing out these resonance structures. So I recommend just pausing the video and kind of reading through all of these instead of me, reading through every single line myself. So I'll give you a second to pause and do that. All right, moving on. So, when trying to figure out which resonance structure is the most ideal, how do we do that? Okay, I mentioned that a couple times, but haven't gone into too much depth with it. So, very generally, in order of importance, resonance forms can be compared to select the most stable form through the following criteria. It has to have as many octets satisfied as possible. Right, so if there's any example of carbon with only 3 bonds and a positive charge, its octet rule is not satisfied, so that is not a great resonance structure. It should have as many bonds as possible, right? So with more pi bonds, for example, the better the structure is. Have as little charge separation as possible, right? So you should lessen the amount of charges you have in general when looking at these different atoms. And any negative charges should be on the most electronegative atom, right? So an oxygen should have a negative charge over a carbon having a negative charge, because that carbons are less electronegative than oxygens. So let's look at an example for this. So with this molecular formula here, right, and so what are the charges on this molecule? Right, the carbon is happy, satisfied. It's three sigma bonds, 1 pi bond. Fine, no formal charge there. On this middle nitrogen, right, if we were to draw in, for example, something with like a lone pair, now it has 1, 2, 3, 4 bonds in a lone pair, so it is violating its octet rule. So we know this doesn't have a lone pair. Oops. And with this last nitrogen here, and it also has a +1 charge, right? Because it has 4 bonds, no lone pairs. It's neutral with 5 electrons, and there are quote-unquote 4 around it that it owns, so it has a formal charge of +1. With this last nitrogen here, right, looks like it has a lot of electrons, but it doesn't really, right? It still has the 8 electrons around it, right? So lone pair 2, another lone pair 4. These, the sigma bond and pi bond here, that's 4 more electrons around it, so it has an octet. But, right, it's neutral with 5, but there are 6 electrons, quote-unquote, around it that it owns. So it has a negative formal charge. What's really important to know here is the molecular formula says it's neutral, right? But there are 2 charges here. And that's fine because the positive and negative charge cancels each other out. So this is a neutral molecule. So if you were trying to draw this on your own, you might have been trying to come up with something that didn't have any charges, which would be impossible to do. So instead we have this positively and negatively charged nitrogens. This is something called a Zwitter ion. But is this the most stable resonance form, right? So we can draw a resonance structure for this. So if we take one of these lone pairs, boom, push it here, we have to break this pi bond, and so we're not making sure we're not violating any octet rules, and we'll push it onto the carbon. So now this carbon has a lone pair. There's only 1 bond here. Now there's a triple bond on this nitrogen. And so the nitrogen hasn't really changed the middle nitrogen hasn't changed in its connectivity, so it is still positive charge, but now the carbon is negatively charged, right? Because it still has 3 bonds, has a lone pair, so it's 8 electrons around it, so it has its octet rule satisfied, but there are 1 too many valence electrons around it that it owns, right? So there's 2 here, 1, 2, 3 is 5, and 4 minus 5 is -1. So this is a negatively charged carbon. So which resonance form is the most stable? So as many octet rules satisfied as possible, every carbon, or every atom here has its octet rule satisfied. As many bonds as possible, right? There's still the same number of bonds, right? So instead of having 2 different double bonds, we have a single triple bond. So the same number of bonds. As little charge separation as possible. The charges haven't separated across the molecule. They're still right next to each other. They're just on different atoms. So that means we have to look at this last one. Any negative charges is on the most electronegative atom. So right, nitrogen is to the right of carbon on the periodic table. So remembering our periodic trends, the nitrogen is more stable with a negative charge than the carbon. So we know that the most stable resonance form has to be this one. There's still some contribution, of course, but the major resonance form is this one because that negative charge is on the nitrogen, right? So we kind of have to go through the whole list to figure that out, and is the quote-unquote least important resonance criteria, but it still helps us decide which one of these is major versus the minor resonance form. So there's a few different types of resonance interactions, as we've kind of already discussed. So let's take a look at some of them and just kind of go through some quick examples. And I'd recommend trying to do these on your own before I go through them. So those will be some good quick practice, and I am going to go through these kind of quickly. So with this first organic molecule here, right, there's a lone pair on this carbon, and so it is negatively charged, right? So remembering, so these are all going to be in line angle formula, so this will also be some good practice to figure out what's going on here. So this carbon here still has one hydrogen on it, but there's a lone pair, so now it's negatively charged, right? So we're not violating octet rules with any of these structures, right? So we can't say, oh, there's two hydrogens and a lone pair, because then that'd be too many electrons around the carbon. So, what happens? Where does the lone pair go, right? It can't go here, right, because this is a sigma bond. If we try to do that, right, this carbon here has two hydrogens on it, and we'd be violating the octet rule. So we can't do that. So instead, it has to go here, right, in between these two carbons. And again, to not violate the octet rule, this double bond, this pi bond, has to go onto the neighboring carbon. So now the negative charge is here. We have a double bond here, and the negative charge is on this carbon. Right. So lone pair on this carbon now, double bond here, and we have our resonance form. And these are pretty much equivalent, so there is no minor or major here for the most part. We can draw the resonance hybrid too, if we chose to. Probably won't do that for everyone, but just to show you here, negative charge, right? So this is the resonance hybrid. Okay, so looking at the next example, so pi bond to positive charge, right? So it would be very incorrect to do this, right? Because remember, the double bond, or the double-headed arrow, is showing electron movement, right? And this is a positive charge, meaning that there is a hydrogen on that carbon and nothing else. There's no lone pair, so it's positively charged. So meaning, when we draw that arrow like that, there's nothing moving, right? Positive charges can't move. It's showing an absence of electrons. So it would be very incorrect to do. So instead, what has to move is the double bond here, right? Because there are, two electrons in that pi bond, higher energy than the sig bonds, that can move and contribute to resonance forms. So we're actually going to show it kind of right in the middle, starting from starting the arrow from the middle of the pi bond right into there, and that's it. There's no other electrons that are moving around. And so this is the final structure, right? And again, there's no difference really in the minor or major resonance forms. Like, they're pretty much identical. So we could say the resonance hybrid looks like this, right? Very similar to the other example, right? The dashed bonds showing partial double bond character, and the partial charge showing equal contribution between each of the atoms. Right, so resonance hybrid. Right. So that makes sense. More examples. So within the pi bond itself, we can have electron movement, right? So looking at this molecule here, where are the electrons going to go, right? So we would show them going this way, right? Having the electrons be on the oxygen is the best spot for those electrons to be for that negative charge we're going to be placing on that oxygen, right? So the resulting structure would look like this. I guess I could actually put 2 lone pairs there just for clarity. And now we see this oxygen, negative charge, and we are showing the hydrogens here, and that's just, again, for clarity's sake, because it would look a little weird without them, I think. And this has a positive charge, right? So, I mean, without even really remembering, right, the rules of resonance, what's the more stable resonance structure, it's kind of obvious even just looking at this, right? But the very first rule, right, is we have to have as many octets satisfied as possible, and this carbon, of course, is not satisfied, right? It only has 3 bonds, no other electrons, only has 6 electrons around it, so it is not satisfied, even though the oxygen is. So this is the major resonance form, and this is the minor. So I spelled that entirely wrong. Minor resonance form. All right, so this next one here, we have this called a benzene, right? So this is an aromatic ring. It has 3 pi bonds and is a ring, so it has a degree of unsaturation of 4. It's just something to know. But looking at this, what resonance form is going to take? Sure, we could kind of move, a double bond onto itself and have a positive negative charge. That wouldn't be super great, right? So let's just get rid of that. So what's actually going on here, and it's kind of neat, is that the double bond, even though I'm drawing it this way, it looks like it's kind of coming from the sigma bond. I'm just kind of doing that because having it drawn inside would look kind of ugly. But that arrow is moving from the pi bonds to the sigma bond between those 2 carbons here. And doing that, right, we have to break this double bond, right? Because just having the pi bond here would be violating the octet rule on that carbon, right? Because each of these carbons has 1 hydrogen on it, right? In order for this structure to make sense and have no major violations going on. So we have to push it here, and likewise, we have to push this final double bond right there. So what does that look like? So now, double bonds have kind of just all moved around. You see, there's nothing really different between these 2 structures, right? They are basically the same. But this is something that happens with molecules like this that are quote-unquote aromatic, and we'll talk about that more a little later. But there's equal, contribution going on between these 2 quote-unquote resonance forms. And so the hybrid, if we so chose to, could be drawn like this. And that is a terrible drawing. The angles are not done well at all. There we go, that's a little better. So we would actually kind of draw something like this. And there's no charges here, right, because we didn't make any charges. But this is just to sort of show that there is just a cyclic flow of electrons all around the benzene ring. And it's kind of neat because it has some interesting electronic characteristics that we'll get more into hopefully at the end of this semester or sometime next semester. But it is a pretty interesting phenomenon with these quote-unquote aromatic molecules. So this last example here, just kind of wanted to go through, there can be multiple resonance forms. And so just keeping things simple, here is another example of a cyclic molecule. This time it's missing, a double bond has a positive charge, right? And again, if you're still kind of confused by some of these line angle formulas, I'd recommend going through and just trying to figure out what does this mean, right? How many hydrogens does this carbon have versus this one and these? But, right, so again, we can't draw positive charges going towards anything else because there's no electrons there, right? So we cannot do that. So instead, what we have to show is the double bond moving this way, right? And it would be incorrect to sort of show the double bond going right onto that atom. because that is A, kind of too far of a leap for those electrons to go, and B, it doesn't really mean anything. So it is better to have it drawn this way, right, showing the pi bond going from this double bond into the space between this carbon and this carbon that has an empty p orbital. So that looks like this. Boom. And then this pi bond over here didn't change. And of course now this carbon down here is now satisfied, right? Before it only had one hydrogen. It was only bonded to 3 things, so it was missing an electron, so it didn't have its octahedral satisfied. But now, unfortunately, this poor carbon up here has that positive charge, right? So we can show another resonance form where the pi bond here is moving to the space between this carbon and this carbon with the empty p orbital. So now, it kind of looks like the opposite of what was there before, but this is the result, right? So the electrons moved from these 2 carbons, placed in between these 2 carbons, and now this carbon is left without that pi bond. So it only has, again, it's only bonded to 3 things, right? These 2 neighboring carbons and the hydrogen that is not shown here. So is there a major resonance form for this? The short answer is no, there's no major resonance form. They're all equally contributing. But this is sort of an example of how there can be more than one resonance form on a molecule. And we could, sort of do something like, now we have, let's say we break this double bond and draw this here. So there's a positive charge here and a negative charge here. But that would just not be a great resonance form at all. Like, sure, it exists, but it would not be something that, would be even a minor contributor, right, to this resonance form, because there's too much going on, too many charges. It's violating another. One of the octets is not being satisfied in the carbon, so it is not a great resonance form at all. So the hybrid for this would look as follows, where you have, partial double bonded character going through the indicated carbons. And so now where's the partial positives on these? They would only be on the carbons that had the positive charge, right? So this top carbon, this carbon to the right, and this carbon to the left. It wouldn't be on these middle carbons here because they never held a positive charge during our resonance forms that we've drawn. So we draw it like this. This is our resonance hybrid. Cool. So I hope that makes sense. I hope going through some of these examples kind of gives some indication as to how to best go about thinking about resonance structures, and how to sort of identify what's major or minor in resonance forms, and when there is no major or minor and they're all just sort of equivalent. And I'm sure we'll be going over more examples of these in class, in order to get some more practice thinking about these, because they will be important pretty much for the rest of your time in organic.